Hi everybody. So in this video we're going to continue with chapter 4, Geometry and Trigonometry 1, specifically into section 4.2, right-angled trigonometry. So in order to understand the primary trigonometric ratios, let's take a look at this right-angled triangle. So first of all, notice that you have a right angle here and that these are the legs of the right triangle, whereas this is the hypotenuse. If you take one of the acute angles, because this angle is 90 degrees, therefore the angle at vertex A and the angle at vertex B are going to be acute. So if you take this acute angle here as a reference, angle theta, then you're going to see that this leg is opposite to theta and this other leg is adjacent, whereas the longest side in the right triangle is known as the hypotenuse. So from this, we can say that for an acute angle theta in a right-angled triangle, we define the following ratios. Sine of theta is equal to the opposite leg divided by the hypotenuse. Cosine of theta is equal to the adjacent leg divided by the hypotenuse, and tangent of theta is equal to the opposite leg divided by the adjacent leg. Now, just so we understand what trigonometry is and where it comes from, think of it this way. Notice that this angle is 90 degrees, and in order for a triangle to be a right triangle, it has to have this angle. So that means one thing. It means that if you look at these two legs as moving pieces that move back and forth and change in size, the hypotenuse is also going to change, right? If we want to have a full triangle. But there is a predictable pattern in this situation. And that predictable pattern led to the creation of tables like the one you see in this illustration. In the old days before calculators, there were trigonometric tables for angles in degrees and decimals. And here's a page of one of these tables. And what you would have is all the different proportions, because in the end, the size of this angle is going to vary in proportion to the length of the sides of the triangle. So that means that you could create a table, and that's what they did, probably as far back as the Babylonians. So notice here in this illustration, we have that the sine of 31 degrees is 0.5150. And you also have the example of 32 degrees where the sine is 0.5299, as we can see here. So these tables were the ones that people would have to use in the old days, engineers or navigators, because you can use trigonometry to calculate distances and so forth. So now let's take a look at example 4.9, and it says find the value of the missing side length correct to 2 decimal places, and this is A. So this is where we come to use the trigonometric ratios. So let's take a look at a couple things here. So this is the angle, 20 degrees. This here would be the opposite side, and this here would be the adjacent, and this is the hypotenuse. So notice that sine of 20 is equal to the opposite, y, divided by the hypotenuse, 4. So with this simple equation, we can solve for y. Notice that y is going to equal sine of 20 times 4, right? That's going to equal y. So all we have to do is plug that into the calculator, and we're going to get that y is approximately 1.37 centimeters. So what can we use to find x? Notice that x is the adjacent, so that would be cosine, right? Cosine of 20 is equal to the adjacent, which is x, divided by the hypotenuse, which is 4. So then this is the same procedure. Cosine of 20 times 4 is going to be x. Plug that into the calculator, and you're going to get that x is approximately 3.76 centimeters. So with B, we have a weird looking triangle that seems to be downwards. But in these cases, all you have to do is be careful and identify the sides correctly. So if this is our angle of reference, this is the 90-degree angle. So notice that this would be the adjacent side. This would be the opposite, and this is the hypotenuse. So that means that they want us to find the hypotenuse. So we have to decide upon which ratio is more convenient. And because we have the opposite, and we want to find the hypotenuse, that means that we can use sine. And we know that sine of 15 is going to be 2 divided by h, opposite over hypotenuse. This is a little trickier to solve because we have the h dividing, but first send it to multiply, and you're going to get that h times sine of 15 is equal to 2, and then send this to divide. So h is equal to 2 divided by sine of 15. And we plug that into the calculator, and we're going to get that it is 7.23 centimeters. So next we have example 4.10, and it says, for each of the following right-angled triangles, find the value of the interior angle theta correct to the nearest degree. So let's look at case A. They want us to find the value of the angle theta. What you have to do in these cases is always identify the legs and the hypotenuse of the right-angled triangle. So this would be the opposite leg, this was the adjacent, and this is the hypotenuse. Remember that the reference is always the angle itself. So which trigonometric ratio can we use here? We have the adjacent and we have the hypotenuse, so we have to use cosine. So that means that cosine of theta is equal to square root of 2 divided by 3. But what we want to find is the angle. So that means that we're going to need an inverse trigonometric function, because this implies that theta, the angle, is equal to the inverse cosine of square root of 2 over 3. If you plug this into the calculator, it's going to give you approximately 62 degrees. Now let's take a look at B. So here we have the angle, and notice that this is the 90-degree angle as well, and that means that this is going to be a leg that is adjacent to the angle. This is the leg that is opposite, and this is the hypotenuse. So we can find theta using sine, because sine of theta is going to be opposite 12 divided by hypotenuse, which is 13. Then again, we proceed to find the angle by using the inverse trigonometric function, and that's going to be inverse sine of 12 over 13. Plug that into the calculator, and it's going to give you 67 degrees approximately. So now let's take a look at C. Here is the angle of reference. Here is the 90-degree angle. So these are the legs. This is opposite. This is the adjacent leg. And this is the hypotenuse. So notice that in this occasion, we don't have the hypotenuse, but we have the opposite and adjacent legs. So we can say that tangent of the angle theta is equal to opposite 8 divided by adjacent square root of 7. So again, that implies that theta is equal to the inverse tangent of 8 over square root of 7. And this is going to be approximately 72 degrees. But before we continue with the next example, let me show you how to use the GDC in these cases. So let's take a look at B. I want to do the inverse sine of 12 divided by 13. Close parenthesis and hit enter. Now notice that I don't get 67 or anything close to it. I'm getting 1.17. If this happens to you, it just means that your calculator is set up not for degrees, but for something called radians. So you want to change it to degrees. We do this by clicking on mode, and then notice that the third function that is listed says radian or degree. You want to pick degree, enter that there, then quit, and let's try it again. So second inverse sine of 12 over 13, hit enter, and there it is. Notice that it is approximately 67 degrees. So now we're going to continue with the area of a triangle. And example 4.11, it says find the area of each of these triangles. So let's focus on letter A. Now let's remember that the area of a triangle is equal to 1/2 the base times the height.
Now, the problem with these triangles, as you can see, is that we don't have the height. But we can solve this by applying trigonometry. Now, notice that if you draw a height from the vertex here, let's draw a dotted line. If it's a height, it should form a 90-degree angle with the base. It should be perpendicular to the base. So with this, let's call this height h. With this, notice that we can say that sine of 30 is equal to the height over 5. But this implies that the height is equal to sine of 30 times 5. Now, once we have this, we can find the area because the area is going to be 1/2 the base, which is 6 centimeters, times the height, which is sine of 30 times 5. Now, in the calculator, you're going to see a parenthesis here, and you don't want to multiply the 30 by 5 directly, right? Okay, plug this into the calculator, and it's going to give you approximately 7.5, in this case, centimeters squared. So now let's focus on B. So first of all, we need to draw a height to the base, and the height is going to be perpendicular to the base. Therefore, we have an angle of 90 degrees. We want to draw the height opposite to the angle that they give us, because this implies that sine, which is a ratio we want to use, of 20 is equal to the opposite, h, over the hypotenuse, which in this case would be 9. Therefore, h is equal to 9 times sine of 20. Now we can find the area because the area of any triangle is 1/2 base times height. So substituting, we would have that the area is going to be 1/2, and now 11 is the base, so 1/2 times 11 times 9 times sine of 20. Plug this in the calculator, and it's going to give you approximately 17 centimeters squared. So in general, we can say that the area of a triangle with an acute angle theta enclosed by two sides of lengths A and B is 1/2 A times B times sine of theta. So notice that we got the same expressions before, right? The only thing that varies here is the order. We have A times B, but notice that it would be the same as what we did before. So this would be, for example, the area in this case would be 1/2 A times 6 times B times 5 times the sine of the angle. And then in this case, it would be that the area is equal to 1/2 A times B. It can be in any order. So 9 times 11 times the sine of 20. So now we're going to take a look at some applications of trigonometry. And let's begin with example 4.12. And it says, an aeroplane flies 400 kilometers on a bearing of 78 degrees from city A to city B. Part A, how far north or south is B from A? How far east or west is A from B? So for this, we're going to use a drawing. So what is bearing? A bearing of 78 degrees from city A to city B. So to find a bearing, what you do is that you start from A, point A, and then draw a line that points to the north, like this one here. And the bearing would be measured starting from that line that points to the north. So 78-degree bearing would be this here, this angle. So that means that this is the direction in which the aeroplane flew, 400 kilometers, until it reached city B. Now notice that that also means that city B is to the north from A. And we need to find Y in order to answer part A. But let's take a look at part B. It says, how far east or west is A from B? So that means that how far is A from B? And notice that this would be west from B, right? West. Okay, so we're ready. For part A, to find Y, we need to use a trigonometric ratio. So notice that it's adjacent. So that means that cosine of 78 is going to equal y divided by 400. And therefore, y is equal to the cosine of 78 times 400. And this is going to give us approximately 83 kilometers. For b, we want to solve for x. So x would be the opposite. That means sine of 78 is equal to x over 400. Therefore, x is equal to 400 times sine of 78. Notice that this is the same thing. It doesn't matter in which order you multiply, right? So this is going to equal 391 kilometers. So for the complete answer, we would say that city B is 83 kilometers north from A, right? So B is 83 kilometers north from A. And for the next one, we would say A is 391 kilometers west from B. So let's talk about angles of elevation and depression. In land surveying and architecture, angles are often used to calculate lengths that are too large to measure. A clinometer is a device that helps measure such angles. Angles of elevation or inclination are angles above the horizontal, like looking up from the ground level towards the top of a flagpole. Angles of depression or declination are angles below the horizontal, like looking down from your window to the base of the building opposite to you. So notice here in figure 4.18, we have an angle of depression and an angle of elevation. So this would be like looking out from the window down to the base of a building. And this would be like somebody at the base of the building looking up to the person that is looking down from the window. Now, the interesting thing about this situation is that the angle of depression and the angle of elevation would measure the same. Okay, so now let's continue with example 4.13. And it says, the Burj Al Arab luxury hotel in Dubai, United Arab Emirates, is located on an island 280 meters from Dubai Beach. A land surveyor who is 1.78 meters tall, standing at the shore of Dubai Beach, measures the angle of elevation to the roof of Burj Al Arab to be 36.6 degrees. How tall is the Burj Al Arab? So for this, we're going to use a drawing. Now the person would be standing here, the surveyor, and this is the building. Notice that the person is 280 meters away from the building, standing on the beach. And we also have to take into account the person's height, the 1.78 meters. So since what we want to find is the height, and we have the angle, and we have the base, so that means that we would need to use tangent, right? So tangent of 36.6 is equal to h, opposite, over adjacent, 280. So again, this implies that h is equal to 280 times the tangent of 36.6. And this is going to give us approximately 208 meters. So adding the height of the land surveyor would now give a real total height of about 210 meters. So next we're going to take a look at something called exact values of trigonometric ratios. And we'll do so by taking a look at example 4.14. And it says, by constructing appropriate right-angled triangles, find the exact values of sine, cosine, and tangent for theta equal to 30 degrees, 45 degrees, and 60 degrees. So take a look at these two figures. First, figure A is a square. Notice that the square has lengths 1 for each side. And then if we draw a diagonal, we would get a right-angled triangle here to the right, also to the left, but let's focus on this one to the right. And the hypotenuse would be equal to the square root of 2.
Now, in this case, notice that sine of 45 is going to equal 1 over square root of 2. Cosine of 45 is also going to equal 1 over square root of 2. And then tangent of 45 is going to equal opposite over adjacent, which is going to equal 1. For B, notice that we have an equilateral triangle with side lengths 2. We draw a height, and because it's a height, it's going to form a 90-degree angle with the base. And it's also going to split it into two equal triangles, because this angle here that used to be 60 is now going to be 30 degrees. That means also that this side length is going to be 1. So from here, we can find the trigonometric ratios for 60 degrees and 30 degrees. So notice that sine of 30 is going to equal 1 over 2, or 1/2. Cosine of 30 is going to equal square root of 3 over 2. And then tangent of 30 is going to equal 1 over square root of 3. Then we have that sine of 60 is equal to square root of 3 over 2. Cosine of 60 is then going to be 1/2. And tangent of 60 is going to equal square root of 3 over 1, or square root of 3. So these are what are called the special right triangles, and these ratios are the fundamental ones in trigonometry. So I would suggest you memorize them.